Collision detection and collision avoidance have become essential components in robotics systems for safe human-robot interactions. With the arrival of Industry 4.0, an increase in robotic systems has emerged in manufacturing, creating more environments where people and robots collaborate with each other. In order to guarantee the safety of the users and the robots, these components need to work in real time. Many approaches use geometric volumes to model the robot and detect collisions between objects. Models such as bounding spheres, axis line bounding boxes, oriented bounding boxes, and bounding cylinders are used as an abstraction of the robot's true model and provide fast approximations. However, they achieve this at the expense of conserving the true form of the robot, losing the ability to get the true distances between objects. The GGK and RGGK algorithms are methods for accurately calculating the distance between meshes. The Flexible Collision Library is an open-source collision detection library which implements the GGK algorithm, but is not fast enough to be run in real time. Our proposed method is an out-of-the-box, highly accurate real-time collision detection system that requires only the URDF of the robot and object meshes with their respective transformations to generate a model of the robot's environment. The system uses a variant of the recursive Gilbert-Johnson-Curthy algorithm to return the shortest distance between all the pairs of objects, which is used to determine collisions. The mesh models are imported as graph data structures. Using the adjacency list of the graph, we can take advantage of the RGGK algorithm to reduce the computation time of the shortest distance between a pair of objects. To place the components in the environment, we use 3D transformations to translate and rotate the mesh models to the position they occupy in reality. For the robot links, this is done with the forward kinematics of the robot. For the objects in the environment, this is done by the transformations provided to the pipeline by the user. At each time step, the model is updated by using the forward kinematics of the robot and a backup of the graph representation of the links. The new graph is used in the model, while static objects in the environment are kept as is, since they do not need to be updated. This minimizes the amount of computations required to have the environment model for each time step. We use a variant of the RGGK algorithm that uses a simpler approach to the distance sub-algorithm. In previous work, the barycentric coordinates were used to compute the distance. Here, we use simpler principles from linear algebra. This cuts the total computation time. For details, please see section 3b of our paper. The performance of our collision detection system is compared to the flexible collision library used in the robot operating system. We compare their performance on the self-collision detection of the KUKA LBR IWA and the Mechademic Mecha 500. From our results, we can see that our method greatly outperforms the flexible collision library, taking less than 1% of the computation time that FCL requires. We also notice that our method is also better at adapting to more complex models. In summary, our system works in real time, only needs the URDF and objects with their transformations, is easily integrated to any robot, and is 100% accurate.